Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of a series on exponential and logarithmic functions, specifically exponential functions. You should have watched the previous two videos. One is a review of exponential functions. The other is just the types of exponential growth and decay that you would see. I should also make the note that I've mentioned in the previous videos that it is assumed, since you are in college algebra, you have strong experience with exponential and logarithmic functions. So some of the examples I use will be somewhat higher level, but still I do embed review because you are still one course away from having learned this material. And so it's nice to kind of see it again. So let's go ahead and talk about finding equations of exponential functions. So our example here, on January 22nd, 2020, there were 313 confirmed cases of COVID-19 worldwide. As of September 27th, 2020, there are, because I wrote that today, 32,929,407 confirmed cases. Build an exponential model representing this situation and state the daily growth rate, the daily growth rate, the daily growth factor, and the monthly growth rate. So some of these pieces of language here you may not be familiar with. We'll introduce those as we move forward. So when somebody says build a model, you can at least say, well, our time zero number, I guess you could say, would be at time zero, which is January 22nd, there were 313 cases. And then sometime later, there were 32,929,407 cases. We just need to know how many days are between January 22nd and September 27th. And a quick computation yields 250 days. So the 250 days have passed since January 22nd, and now we're at 32,929,407 cases worldwide. And now the question is, build an exponential model representing this situation. The nice thing here is that we have what is called the vertical intercept, the time zero value. Remember, all exponential models that are worth any weight are of the form P of t equals P naught b to the t. P naught being the initial value. So the time zero value here is 313. So I'm going to go ahead and say this implies that our population at any given time is 313 b to the t power. So now I have actually used this point. I no longer am going to use it. I'm going to switch and move on. So figure out how to use the second point, which I'll highlight in a different color here. You just need to know that it should satisfy this exponential function. And therefore, we can say if the input t is 250, then our output p of t should be 32,929,407. So let's go ahead and insert those values in there just by doing a substitution. So we have 32,929,407, and that is equal to 313 times b, some base, to the 250th power. We want to solve this for the base, so we want to know what the base of this function is, and that just involves dividing by 313 so that we get this ugly number. And you just kind of have to, in the real world, get used to numbers that are somewhat bulky. That's totally fine. And this is a great precursor to solving exponential equations, because a lot of people will see something like this and think, I have to take logarithms of both sides. And we have not even begun talking about solving exponential equations, and you don't need to use some exponential solution technique here because this is not an exponential equation. Notice that the unknown is actually not in the exponent. This is what we call a power function or a polynomial equation. You would just raise both sides to the 1 over 250th power. That's what I'm going to go ahead and do. And I'll mark it this way. I'll say this implies when we raise both sides to the 1 over 250th power that you get the left-hand side to the 1 over 250th power. Just kind of sneak that in there real quickly. There we go. And equals to the right-hand side. Of course, 250 divided by 250 is 1. There's a little caveat here, by the way. The caveat, before anybody yells at me, is that if you take the even root of an even power, that should be the absolute value of that b. Let me state that again clearly. If you take the even root of b raised to the same even power, then it should return the absolute value of b. That's just from our algebra prerequisite. But here's the deal. B is positive. To become the base of an exponential function, it has to be positive. So we don't have to worry about forcing an absolute value here. All right, so let's go ahead and just grab a calculator really quickly. And when everything's said and done, this will imply that B is approximately 1.04, I'll go to 3 digits, 1.047. That's very rounded, by the way, but good enough. So our base of our exponential is that. Now, I still have that number, not the exact, but the approximated number, more digits in the calculator. So I'll come back to that in a moment. But for now, let's go ahead and showcase this. You know what? Now that I'm thinking about it, let me showcase this using Desmos because I want to show you how important it is to use exact numbers. So here I am on Desmos's main page. I'll just click on Math Tools, and I'm only going to use a scientific calculator, not the graphing calculator. Mainly because I don't need the graphing calculator, and there's just too much extra stuff involved there. So what I'm going to say is that B is going to equal to, and that's the nice thing about Desmos's scientific calculators, you can assign variables in there. B is going to equal to the quantity 32,929,407 divided by 313, and that's raised to the, I'll start a parenthesis, 1 over 250th power. And now you can see it's got a nice expansion there. We are going to go ahead and use that in a little bit. All right, so I'll hit enter to save that. Now that we have that done, let's go ahead and go back to the other page. So back on this page, we're going to go ahead and say, great, our population function P of t, this is the population of people who've been diagnosed with COVID-19, is equal to 313, I should say is roughly equal to, by the way, is roughly equal to 313 times the quantity 1.047 raised to the t power. Now, that's a rough approximation, not exactly correct, but it's close. State the daily growth rate. Well, if you think about this, t is in days. That's what the units for t are, days. So our daily growth rate, as we know from the previous video in this series, this can be written as 1 plus 0.047. So our daily growth rate implies it's roughly 4.7%, because it's 0.047 as a decimal, and you move the decimal place over to get what the rate is in actual percent. So about 4.7% increase on a daily basis from January 22nd to September 27th. The second part of this, And I'll highlight out what we've actually done. So maybe I'll underline it. So daily growth rate, we're done with. And the daily growth factor, well, we're going to be done with it very quickly here, because the daily growth factor, as stated in our previous video, is actually just this number right here. So I will write that down below, that the daily growth factor is roughly 1.047. You have to say roughly there because it really isn't exactly that. And now our final question is concerning the monthly growth rate. In other words, over the entire month, what is the increase in the number of diagnosed people or confirmed cases of COVID-19? And I chose this to really highlight what you're going to do as you move forward when you have to change bases for exponential functions. Generally speaking, you're changing from like maybe a base 2 or a base 1.2 to the base e. That's almost always how it's going to work. But in this case, I'm going to change to a completely different base that I don't know. Let me show you how that's done. So right now, our current base is 1.047 roughly, and it's to the t power. And remember, it has that growth factor per 1 day. And again, if you don't know that, watch the previous video, because in the previous video I talk about the fact that this denominator is the per 1 day in this case. But if you want to know the monthly growth rate or growth factor, you'll look at a completely different base to the t over 30. In other words, I want to know what is the base that I would have if I allowed it to grow every 30 days, per 30 days. I want them to be equivalent. In other words, at the end of 30 days, I want that same number of people who got sick to be, I want that number of people who got sick to be the same in both cases. So we need that b to the t over 1 to be the same as c to the t over 30. Well, if you think about it, the t's don't really matter. They share them in common. There's no need to worry about that. So I'll go ahead and get rid of that. And maybe I should even justify it a little bit further by saying, look, this is just b to the 1 raised to the t, right? And the right-hand side is c to the 1 over 30 raised to the t. But in the long run, the bases should actually be the same. That is, this base is if I only went 1 day, and this base is if I went 1 day out of 30. But it's the same thing. You've gone 1 day in both cases. So b to the first must therefore be c to the 1 over 30th power. Well, b, remember, is very roughly 1.047. C we do not know, but we know that if we raise both sides to the 30th power, we'll find out what c is, approximately. Now here's where I find it very important. I'm going to raise both sides to the 30th power. Here's where I find it very, very important that you use some type of graphing technology that can save your work. And that's just because we have b over here. And if I just type in b, and we're going to raise that b to the 30th power, that'll give us a much more accurate view of what the growth factor is. B to the 30th is roughly equal to 4.005. You know what? And I think 4.005. We'll just keep it rounded to 3 decimal places here. So I wrote that down over here. I just raised both sides to the 30th power. If you need to see that in action, I raised this side to the 30th, and this side was b, and I just raised it to the 30th. We computed that in Desmos, and it's 4.005 roughly. So what does that mean if I told you that c is 4.005? Remember how c was built? We had some population function where we had an initial population, doesn't really matter. and then c to the t over 30. That is, after every 30 days, we multiply by c. So that's our monthly growth factor. It takes 30 days to get all of c, right? If you let t equal 30, you would see that you would have c to the 30 over 30, or c to the first, or just c. That gives you the full power of c to multiply your population by. So c itself is your once per month growth factor. And so when they ask what's a monthly growth factor, well, that's pretty nice to write down now. And if you want to know the monthly growth rate, well, remember how to write a rate. C, again, is approximately 4.005, and you would write that as 1 plus 3.005. That is 300.5%. That's the monthly growth rate. So monthly, I'll write that in. Monthly growth rate is 300.5%. Now I have to say, this is our model is fairly accurate for at least up until September 27th. And most people would not want more than just this model right here that we wrote. But this example was meant to get us to think about how to build an exponential function or an exponential model given 2 data points. In this case, the 2 data points were very special. One data point was on the vertical axis. It was the initial value, the time 0 value. And the other one was kind of today's value. Now that won't always be the case. So let's go ahead and take an example of a model that we can build where we're not given the initial value. So here we have an equation, and notice they did not hand us the initial value. They just handed us 2 points on the curve. How do you find the equation for that exponential function that they've given us? Which, by the way, is a decreasing exponential function, a very special type of exponential function. Decreasing exponential functions actually do have a lot of uses, mostly for signal processing, where you dampen down signals. And we'll play with those in this course later on. So how, given this information, would you ever find the equation of the exponential function? Well, one thing I can state easily is that an exponential function usually has this form. I don't have to worry about the t over business. I just want to have it in its basic form, just like this. I also know that I've been given easily 2 points on that curve, both of which should satisfy this exponential function. And so when you're handed a point that satisfies any function, then you can let the output be the y value and the input be the input value, which is a t value in this case. Now, there are several methods for solving this style of problem. But let me tell you, I have a very special method that I prefer, so I'm going to teach that method. Notice how many unknowns are in this equation. We have P naught, we don't know, and we don't know what B is. We have 2 unknowns. And throughout mathematics, the number of unknowns that you have tells you how many conditions you will need, or how many equations that you'll need. So 2 unknowns means I need 2 equations. There's only one right here. However, I can build a second one by using that second point. I could say, well, the output is 2/9 when the input is 3. Now, if you don't mind, I'm going to call this equation 1, and I'll call this equation 2. And I'm going to do something maybe that you've never been taught. Some people like to solve these using substitution method. You can't really use elimination method here, but you can use substitution method from your systems of equations prerequisite from Algebra 1 and then again in Algebra 2. But I'd like to showcase a way that's really cool. You take the equation which has the highest power on the unknown. So specifically, I'm going to take that second equation, and you'll write it as a numerator, sort of. Equations can't be numerators, but just play along with me. So I'm going to take equation 2. Oops, EQN is what I like for equation. So I'm going to take equation 2, and I'm going to say that's 2 over 9, which is equal to P naught b to the third. And I'm going to divide that equation 2 by equation 1. Equation 1 is 54, and on the right-hand side was P naught b to the negative 2. You can totally do this because because these equations are supposed to be both true, and you can always divide true equations as long as they're non-zero. So, and this method really only works well with exponential functions. So let's go ahead and continue the solution process now that we have an equation that involves a bunch of fractions. You can see that on the right-hand side, the P naughts cancel beautifully. Also, you can use a property of exponents to write this right-hand side as b to the fifth, because the negative 2 gets ripped off that exponent in the denominator and it pops upstairs, becomes a b squared times b cubed, becomes b to the fifth. And then finally, I could go ahead and take that 2/9. 2 goes into 54 27 times, so this is 1 over 27 times 9. And if you don't know what 27 times 9 is, I don't blame you, but I do know that that's 3 cubed, and that is 3 squared. So altogether, that is 3 to the fifth. Now, to solve for b, base, I'll raise both sides to the 1/5 power. So I'll raise the left-hand side to the 1/5, and I'll raise the right-hand side to the 1/5 power. The 1/5 power of 1 is just 1, and the 1/5 power of 3 to the 5th is going to be 3. And now I have found my base. The only thing I'm missing at this point is what the initial population is. And you can actually find that using either equation, either the first or the second equation. I'm actually just going to plug it in to the first equation just because I want to. So plugging that into the first equation, I get 54 is equal to P naught, and then I have this b value raised to the negative second power. It's supposed to be a 1. Sorry about that. Negative exponents means that you can flip the argument. So this implies that you have 54 equals P naught times 3 squared, which is 9. I'll divide both sides by 9, and I get that P naught is 6. And so the actual equation that is represented by this curve is going to be P of t, which is P naught, 6, times b, 1/3, to the t power. Probably one of the biggest rookie mistakes that will happen here is that people will say, but 3 goes into 6 twice. 3 goes into 6 twice. That's a no-no. You cannot do that because that 3, it's locked inside of this exponent here. This guy right here, this t, is locking that 1/3 up. You cannot pull things out of that. It's locked. But that is the equation of this exponential function. And nothing else you need to do there. So this is, like I said, a review, but kind of a high-level review of finding equations of exponential functions. In the next video, we'll talk about compound interest.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.